Today we're going to work through problem 4.8 from Taylor's Classical Mechanics. This is a chapter 4 problem. This involves the conservation of energy as well as the normal force. Okay, so it's saying to consider a small frictionless puck perched on the top of a fixed sphere of radius r. That's going to be our radius. There's our puck. And it's saying if it's given a tiny nudge so that it begins to slide down the sphere, it's going to start to slide down. What vertical height will it descend before it leaves the surface of the sphere? So we want to find the puck speed as a function of its height and then use the second law to find the normal force on the sphere on the puck. What value of this normal force does the puck leave the sphere? So what we're going to start by doing here is finding our potential energy function. And if we measure theta going down from here, so that's going to be our theta. Our initial theta is going to be 0. Our potential energy as a function of theta is going to be mgr cosine theta. Our initial potential energy with theta as 0 is just going to be mgr. And we know that by the conservation of energy, our initial energy is going to be the same as our final energy, which is equal to our initial energy is just that potential energy because we don't have any kinetic energy to start. Puck is at rest. So our initial energy is going to be mgr. That's going to equal our final kinetic energy and our final potential energy summed together. So this represents our final potential energy. This represents our final kinetic energy. Now we can make an expression here. mgr, 1 minus cosine theta, equals 1/2 mv squared. Or 2 mgr, 1 minus cosine theta, equals mv squared. Now this is going to come into play just a second here when we need to use the conservation of energy to find its speed as a function of its height. Now we need to use the second law to find the normal force of the sphere on the puck. So if the puck is placed here, you're going to have a normal force coming out, and we're going to have the force of gravity going down here, mg cosine theta. Now, the normal force minus that force of gravity must be equal to the total force, which we know that the total force is mass times acceleration. In our case, we have centripetal acceleration, which is v squared over r. And because that's going to point inwards, I'm going to put a negative there. So we have a negative mv squared over r to represent our mass times acceleration. Now, this is where this equation up here comes into play. We now have an expression for mv squared. So our normal force minus mg cosine theta is equal to 2 mgr, negative 2 mgr over r times 1 minus cosine theta. You can see those r's are going to go away. We have the normal force minus mg cosine theta is equal to negative 2 mg plus 2 mg cosine theta. So our normal force is equal to 3 mg cosine theta minus 2 mg. And we can factor this out to say that our normal force is equal to mg times 3 cosine theta minus 2. So that's our normal force. To find the point at which the puck leaves the surface of the sphere, we know that as long as the puck is on the sphere, the normal force is going to counter the push that the puck has against the sphere by pushing outward from the sphere. So our normal force is going to be positive when on the sphere. Now, as soon as the puck that's on the sphere, we're going to have a positive normal force. As soon as the puck leaves the sphere, for a moment, we're going to have a zero normal force for an instant in time between leaving and the normal force will reverse and become a negative normal force. So we know that when the normal force is negative, the puck has left the sphere. So to find the point at which that happens, we can find where the normal force is zero. So using that equation that we just found, we know that our mass is not zero and gravity is not zero. So we can divide out by that. We're going to end up with 3 cosine theta minus 2 equals 0. So cosine theta equals 2 over 3. The theta equals our cosine of 2 over 3, which turns out to be about 48.2 degrees. So this is the point at which the puck will leave the sphere. So the puck will start at the top of the sphere. We're going to give it a slight nudge that direction. It's going to move down here. And somewhere around 48.2 degrees. So that's going to look something like this. At this point on the sphere, the puck will leave the sphere and just begin falling on its own to the ground. So if we want to find the vertical height through which this has descended, what we're asking for is this change in height right here. Where? Let me just expand this out here. We're going to have that. Our circle. You draw a better circle than that. Let's see. I have a circle. There's our initial position. There's our position where it's going to leave the sphere. And we know that this angle right here is 48.2 degrees. This is R, and we are looking for this change in height right here. This change in height. So we know that this value R is the same as R cosine theta initial, which is just 0, so we just get R is our initial height, right? And our final height is going to be R cosine of 48.2 degrees is our final height. So our change in height is going to be R cosine 48.2 degrees minus 1. That's going to be our change in height, and the absolute value of that is going to be the vertical distance descended before the puck leaves the sphere. From where we got this theta value from, we know that cosine theta is going to be 2/3. So our change in height is going to be R times 2/3 minus 1, which is 1/3. R is that absolute value of our change in height. So it's going to fall 1/3 of the radius before leaving the sphere.